Hello, I'm Nick Narati,
I'm Omar Nafi.
I'm Dominic Savarino.
and we designed a mechanical device to transform the motion of ocean waves into usable energy.
As the buoy moves with the rhythm of the waves and tides, it exerts a torque on the connected gear. This gear then undergoes a reduction, driving the pinion and slider crank mechanism, which is harnessed by a linear generator to convert the sea's natural flow into usable energy.
For analysis, we chose to look at the spur gear set, a bearing centered on the pinion, and a shaft connecting the buoy input to our gears. The input to our system is the up and down motion of ocean waves, and our output is a linear motor from Iris Dynamics. The motor was chosen because it is fully backdrivable, meaning it takes incoming forces as a means for supplying power. The motor's spec sheet also provided the velocity, force, and power requirements for the entire machine. The bearings used were found on McMaster, and the gear configuration was found on Rush gears. Given the maximum speed from the linear generator's spec sheet, we used planar dynamics to calculate the angular velocity of the pinion gear.
Dividing the maximum power output of the generator by the angular velocity gives us the torque, which is used to calculate the loads acting on the pinion. In our design, we opted for larger gears so we could mount the slider crank mechanism directly to the pinion, providing sufficient displacement while increasing the output velocity through mechanical advantage. These large gears also provided ample space for a shaft size yet to be determined to support the buoy. However, future iterations will incorporate a compound gear train with smaller gears and a linkage on the pinion shaft to achieve the desired slider displacement. We assessed gear tooth durability against fatigue fracture using AGMA standard equations for bending stress, finding the factors, and computing. Followed a similar approach to calculate the surface stresses. We then found the bending and surface fatigue strength given the material and project requirements such as life and reliability. This analysis revealed our safety factors were higher than necessary. Consequently, we've reduced the gear face width to 1/4 inch, striking a balance between cost efficiency and maintaining sufficient safety margins. With these adjustments, our gear should have a 99% probability of lasting the desired 25 years before surface pitting on the pinion or gear begins.
Due to the tangential and radial loads from the gears, the pinion bearing will experience a radial force of around 31 pounds. The bearings picked for the design are steel sealed ball bearings with a dynamic load rating of 740 pounds, which led us to find a fatigue life of around 10 to the 10 revolutions, indicating infinite life. We chose this bearing to reduce the effects of corrosion, as this assembly will be located in an outdoor environment. The pinion is required to move at around 6 radians per second, which means the bearing is built for 420 years of revolutions.
The gear shaft is subject to a fluctuating weight force, stemming from the beam that connects it to the buoy. In a state of static equilibrium, this force is approximately 617 pounds force, which we'll use as our baseline or mean force. However, this is not constant. It varies in response to the buoy's vertical movements influenced by dynamic buoyant forces. To accurately represent these movements, we've utilized wave data from Maroubra Beach in Sydney, creating a simplified model of ocean wave motion. Through the process of differentiating this model twice, we're able to determine the maximum vertical acceleration. When this acceleration is multiplied by the system's weight, it yields the alternating force exerted on the shaft, which is approximately 104 pounds force.
By analyzing the forces on the shaft, we were able to derive corresponding mean and alternating moments. Opting for an 8.375-inch shaft length, we positioned the buoy arm center at 4 inches from the left of the bearing support, and placed the gear as close to the supports as possible to reduce the length of the cantilevered shaft holding the pinion gear. Our analysis, addressing thrust from gear meshing, radial gear force, and buoy arm force, involved breaking down the shaft examination into Y and Z planes. Calculating the radial and thrust forces combined with buoy arm force allowed us to determine the reaction forces at the bearings in both the Y and Z axes. This approach enabled us to identify the maximum moments for mean and alternating forces in the Y plane. Additionally, we assessed the Z-axis for separation force-induced moments, resulting in a negligible value that wouldn't contribute significantly to the mean moment. We chose 420 stainless steel for its corrosion resistance and high-strength properties, and having an ultimate tensile strength of 110,000 psi. Applying a safety factor of 2, we utilized the general shaft diameter formula, yielding a required diameter of 0.721 inches. However, recognizing the significance of our buoy's arm size, we increased the shaft diameter to 3 inches to ensure a robust connection between the shaft and the arm.
Because the linear motor will be experiencing fluctuating forces, we also performed a fatigue analysis of the shaft attached to the motor. The stress acting on the shaft is due to a 26-pound axial force provided by the motor's spec sheet at the chosen velocity. Considering this axial stress, we used the properties of the shaft material to show its fatigue life with SN and Goodman diagrams. We then found that our alternating stress state of 8.4 psi was well within the boundary for infinite life.
This project significantly deepened our understanding of the iterative design process and wave energy conversion. Initially, we explored models that incorporated interesting mechanical systems such as the slider crank, though as we progressed, the potential for more advanced and efficient solutions became evident. Should we do this project again, we'd spend far more time on the brainstorming phase, outlining the pros and cons of various ideas and systems.
Several concepts have piqued our interest for future iterations of this wave energy device. One idea is to replace the linear generator with a gear train system coupled to a rotary generator. Another concept involves transitioning from a gear-based system to a hydraulic system that would convert stored pressure into electricity.
Another lesson learned is the benefits of automated calculation tools. As this process is iterative, manual recalculations proved inefficient. Future projects will benefit from integrating software or online calculators for better accuracy and efficiency. Thank you for your time and attention.